Hi there. This is the 11.6 video where we're going to be determining if a series converges using some new tests. They're called the ratio test and the root test. Please be aware that in the homework for 11.6, they will also ask you questions about conditional convergence and absolute convergence for alternating series tests. I did several examples of those in my previous video on 11.5 because that's when we start introducing alternating series and doing conditional absolute convergence. So if you'd like to know more about conditional and absolute convergence, please see my previous video on section 11.5. In this video, I'm going to be focusing on the other questions 11.6, which is about using the ratio test and the root test. So as always, let me try to give you some information about what these things are, so you can at least have an idea of what kinds of math formulas we're going to be using to solve these problems. So these are, again, tests for convergence. So we're looking at a series and determining whether it converges or not, converges or diverges. And the first thing we're going to be doing is called the ratio test. The ratio test is actually used quite a lot more than people realize when they first learn it. It is a go-to test because it's easy to perform. And so a lot of people use the ratio test, and it works on very complicated formulas as well. So it's quite versatile. Okay, so what does this great, fantastic, usable series test do? What does it tell us? Well, we're going to take the limit of some terms. So we're not looking at the series anymore. We're not looking at the sum of all the terms. We're looking at the limit of the sequence. Much easier to find limits than it is to find whether a series adds up to a number or not. So this is one of the advantages. We're looking at a limit. We're going to look at the limit of the terms, the n plus 1 sequence divided by the n sequence, which sounds really weird and complicated at first. But all we're putting in is we're putting in the original sequence with n plus ones in all the places divided by the original sequence with n's in all the places. Once I show you an example, it'll become very, very clear. We're doing the ratio of the n plus 1th term sequence divided by the nth term sequence. So I know it sounds kind of confusing, but trust me, when you see an example or two, you're going to like, oh, that's all I have to do. That's all you have to do. So let me show you that momentarily. So if you do this ratio, if you do this limit of this fraction, n plus 1 over n, and you get a result, any result which is less than 1, we immediately know that that series converges. And this is called the ratio test, right? So take a limit of this fraction. If you get less than 1, boom, we know the series converges. If you get greater than 1, we also know something. We know, in fact, the series diverges. So if you, any number less than 1, immediately converging, immediate number greater than 1, immediately diverging. Unfortunately, if it's equal to 1, we don't learn anything. So you only learn something if the limit's less than 1 or greater than 1. If its limit's equal to 1, then we don't learn any new information. So it is possible where you take this limit, you get 1, and you don't really know anything. So that means you have to use a different thing than the ratio test. You have to go to use a geometric test or an integral test or something. So it's possible you wasted your time a little bit because it wasn't either less than 1 or greater than 1. But as I said, it's often easy to do and very, very worthwhile if you do get something less than 1 or greater than 1. So that, my friends, is called the ratio test. The root test is somewhat similar in design. We are again taking a limit of a sequence. We're not looking at the series anymore. And this time we're doing to an exponent of 1 over n. So we're taking our sequence. We're getting rid of all the negative signs in both situations. That's why there's absolute value bars. But here we're doing it to the 1 over n exponent. So you take this limit of the sequence to the 1 over nth power. And if you get something less than 1, we know the original series converges. If you get something greater than 1, we know the original series diverges. And once again, if you get equal to 1, then you don't know anything. You don't get any new information. So it's possible you didn't learn anything. But this is called the root test. You do this sort of nth root. Maybe it should be called the nth root test. But you do this limit of the n, 1 over nth root. And if you get less than 1 or greater than 1, you immediately know it converges or diverges. All right, so as I promised, let me show you some examples so you can see the madness of my explanation. At least how perhaps it's much more straightforward to do than it is to say. All right, so my example here, little a, we have this series right here of 10 to the n over n plus 1, 4 to the 2n. It's a pretty complicated series. Not easy. It's not really a geometric series. It's not a piece series. It's not easy to integrate. There's not a lot of stuff here. You could do using the squeeze principle or the comparison test, but I'm going to show you doing the ratio test. So the ratio test. So we're going to do the limit as n goes to infinity of a n plus 1 over a n. And there's absolute value bars here, but the only reason we have absolute value bars is just to insist that if there were anything negative before, get rid of all the negatives. It doesn't matter the negatives, it works the same way. So we're doing an plus 1 over an, absolute value bars, just to make sure there's no negatives. So I'm going to get rid of the absolute value bars because there's no negatives in this thing. 10 to the n. If you want to write out a couple terms, which I always advocate, 10 to the 0 is 1. You get 1 times 4 to the 0, which is 1. So you get 1 over 1 times 1. If you stick in n equals 1, you get 10. And you get 2 times 4 to the 4. So this is what the terms of the series look like. They're all positive numbers. We don't have to worry about this. So an plus 1 over an. So what does that look like? Let me write my limit thing before I forget. All right. Remember, the top part is the an plus 1. The bottom part is the an, right? Those are the top and bottom parts. The an is literally just the series. It's just this formula right here. So I'm going to fill in the bottom part right away. So it's 10 to the n over n plus 1, 4 to the 2n. That's literally just an is the formula. So the bottom part is just the exact same formula you start with. The top part is the same formula, but n plus 1 in place of n. So what does that look like? We're going to have 10, but not just to the n. We're going to have it to the n plus 1. Right? We're putting an n plus 1 in place of n. This is the formula. Remember, 10 to the n becomes 10 to the n plus 1. N plus 1 becomes, well, n turns into n plus 1. So this becomes n plus 1 plus 1, right? The n turns into n plus 1. There's still a plus 1. And on the bottom, we have 4. And instead of 2 times n, we have 2 times, yes, n plus 1. So we literally just put in the same formula, but we replace n with n plus 1 each time. And then we need to take the limit. Now, this seems like a complicated limit to take, but because we have a fraction divided by a fraction, we're going to be able to simplify this pretty easily. So check this out. We know we can flip and multiply. So I'm going to write this as the limit. The top part is just going to be our 10 to the n plus 1 over, I'll write this as n plus 2. N plus 1 plus 1 is n plus 2. And 4 to the 2n plus 1 is, well, 2 times n is 2n plus 2. So we write this as 2n plus 2. There we go. So that's the top part. And then times the bottom, we're just going to do the reciprocal and multiply. So the bottom becomes, instead of 10 to the n over this thing, it'll be the thing on the bottom over 10 to the n, like that. All right, so now this is where all the nice simplification comes in. We have 10 to the n plus 1 on the top, and we have 10 to the n on the bottom. If you have, you go back to your pre-calculus work, right? If you have 2 power functions, you have 2 exponentials, the bases are the same. We're dividing those 2 powers. You subtract the exponents. So if you take n plus 1 and subtract n, what do we get? We get 1. So this 10 to the n plus 1 over 10 to the n becomes just 10. So this becomes 10. That's this part, and this part simplifies to just be 10. Maybe I'll put that in black here to color code it like that. Well, we could do the same thing with this 4 to the n plus 1. Let me do that in blue, I guess. 4 to the n plus 1 and 4 to the n. Again, we have two powers, same bases. They're being divided. We subtract the exponents. So we have 2n on top, 2n plus 2 on the bottom. We subtract those two. We get 4 to the 2 on the bottom, or 4 to the negative 2 on the top. I'm going to write 4 to the 2 on the bottom. I think most people do it that way. But if not, you would get 4 to the negative 2 on top, and you just bring it down to the bottom. By the way, 4 to the 2 is 16. So it simplifies again very, very nicely. This and this simplify just to be 4 squared on the bottom. And lastly, we have an n plus 1 and we have an n plus 2. Those don't really simplify because of the whole plus thing, but we're going to be able to find the limit of this very, very easily. In fact, we get infinity over infinity. We can use L'Hopital's rule. L'Hopital's rule allows us to simplify a limit that is an indeterminate form, like infinity over infinity. So we differentiate the top and the bottom functions separately. The derivative, well, the 10 doesn't matter. The derivative of n plus 1 is just 1. And the derivative, well, 4 squared doesn't matter. That's 16. The derivative n plus 2 is just 1. So it's 10 over 16. This is a number divided by a number. There's no n's anymore. So this limit is equal to 10 over 16 or 5 over 8. That's our limit. So I just wanted to show you how we started with this very complicated series, 10 to the n over n plus 1, 4 to the 2n. We wrote a to the n plus 1 on the top. We wrote an a to the n on the bottom. We used our algebra skills to simplify this, and the limit was very easy to compute. We used L'Hopital's rule and just got rid of the n plus 1 over n plus 2, and the limit was equal to 5 over 8. So now let's review what the ratio test tells us. According to the ratio test, if you take this limit and the limit is less than 1, we know our series converges. And by the way, if it's greater than 1, we know it diverges, right? So less than 1, it converges. Greater than 1, it diverges. So what did we get? We got 5/8. And I will tell you, I'll let the cat out of the bag. I'll tell you the secret. 5/8 is in fact less than 1. So because it's less than 1, we immediately know that our series will converge because of our ratio test. So this original series, 10 to the n, n plus 1, 4 to the 2n converges by the ratio test. There we go. So that is the first example of using the ratio test. And honestly, they don't get a lot more complicated than this. This is kind of what the ratio test looks like. I started off with a complicated formula. I didn't start off with something really simple. As you can see, it's got all kinds of stuff to deal with, and it simplifies quite nicely using the ratio test. And we got the knowledge that the limit is less than 1, so therefore it converges. All right, let's do a few more examples with some different kinds of things in there just to make sure that you're not surprised when you get to the homework. All right, so my second example here, my little letter b, I have a factorial, which a lot of people will remember. N factorial, let me just write a space here. N factorial means we're starting with the number n, and we're multiplying by one smaller than it, and then one smaller than that, etc. And if you don't stop until you get down to 1. So some people write 3, 2, 1 at the end just to emphasize it goes down to 1. So 3, 2, 1 if you want, but it just keeps going down to 1. If you want an example, then like 5 factorial would be 5 times 4, and you keep going down until you get to 1. And the one other thing that you may not remember from your knowledge, from your study of factorials, is that 0 factorial is basically defined to be 1. It doesn't really make sense because you can't start with 0 and go down to 1. But if you just accept this definition of 0 factorial equaling 1, then our formulas work out really nicely. So this is just by definition. You don't have to do it if you want to, but then your math work becomes a lot longer and you get the exact same answer anyway, because you have to treat it separately in your formulas. So your formulas get more complex, but you get the exact same answer anyway. So math people just say, hey, let's make it equal to 1. it's going to get the same answer, even though it looks a little weird. It doesn't really matter. So I'm going to do the same thing as the textbook author does the same thing. 0 factorial is just going to say it's going to be 1. All right. So in the example we have here, we have a factorial. That's why I went on this little side to explain factorials. So we have n equals 0 to n equals infinity of n factorial over 5 to the n. So writing out some terms, this would be like 0 factorial over 5 to the 0. 0 factorial is 1 over 5 to the 0, which is 1. And then we get 1 factorial over 5 to the 1, which would be 1 over 5. And then we get 2 factorial over 5 to the 2. 2 times 1 is 2. 5 times 5 is 25. And I'll do one more. 3 factorial over 5 to the 3rd. 3 factorial is 3 times 2 times 1, which is 6. And the bottom is 5 times 5 times 5, which is 125. All right. So as I said, maybe write out some terms just to see what's going on here. So the terms are 1 1/5, 2 25ths, 6 over 125, etc. So let's practice again the ratio test. So the ratio test, we're going to do the limit as n goes to infinity of a n plus 1 over a n. And absolute value bars, again, there's no negative numbers, so we don't care about the absolute value bars. Okay. So let's write it out. Okay. So the bottom an is just the formula. So this is just n factorial over 5 to the n. The bottom is the an is just the formula. The top is the formula where I have n plus 1 instead of just n. So instead of n factorial, I'll have n plus 1 factorial. And instead of 5 to the n, I'll have 5 to the n plus 1. So I've written this with n plus 1s instead of n's on the top. I forgot my limit sign. I'm going to give myself -1 points if I forget the limit sign. Okay, so there's my an plus 1 on the top and my an on the bottom. I'm going to use my algebra to simplify this. I'm going to leave the top thing on the top. So n plus 1 factorial over 5 to the n plus 1. And the bottom, I'm going to flip and multiply. So I get 5 to the n on top and n factorial on the bottom. Okay, so that's my algebra there. And you can kind of see, as before, we have a 5 to the n plus 1, which is a exponential with base 5. And we also have this power term with base 5, 5 to the n. And we know that if we have two exponentials, they share the same base, and they're being divided. We just subtract the exponents. So n minus n plus 1, we get a -1 or just 5 on the bottom. So this and this are going to simplify with just 5 to the -1 or just 5 on the bottom. All right, what about these crazy factorial things? I recommend that people write these out, because until you do a bunch of factorial problems, they seem a little mysterious. So let me write out n factorial on the bottom. N factorial is, again, n minus 1, n minus 2, all the way down to 3, 2, 1. That's what n factorial is. You start with this number n, and you keep going down. So what is n plus 1 factorial? N plus 1 factorial means you start with n plus 1, and then you get one smaller. So what's one smaller than n plus 1? Like, we started with n, and then one smaller was called n minus 1, and one smaller than that was n minus 2. So if you start with n plus 1 and you do one smaller, what's one smaller than n plus 1? And the answer is n. And then what's one smaller of n? N minus 1. So again, we're just subtracting 1 every single time. N plus 1 minus 1 is n. N minus 1 is n minus 1. And then n minus 1 is n minus 2. We go all the way down to 3, 2, 1. And you may now see more clearly that most of this just divides out. The 1s, the 2s, the 3s, the n minus 2s, the n minus 1s, the n's, all that goes away. All that divides to weak 1. The only thing left over is n plus 1 on the top. And of course, we still have that 5 on the bottom. All right, so this is equal to, the limit as n goes to infinity. All the stuff on the top becomes n plus 1. On the bottom becomes 5. Okay, so we still got to take the limit. So what happens as n goes to infinity of n plus 1? Well, you get infinity plus 1, which is infinity. The bottom has no ends in it, just a 5. So it's infinity over 5. So what is the limit as n goes to infinity? It's infinity divided by 5, which is infinity, or definitely diverging, right? So what does our ratio test says? It says if the limit is a number, whoops, that's the root test. One more. There we go. If the limit is greater than 1, which is infinity is definitely greater than 1, then we know that our series diverges. So now we know that the second example diverges. Thus, we know that our original series in the n factorial over 5 to the n diverges by the ratio test. There you go. So again, throw in some complicated looking formulas using the ratio test. They oftentimes simplify quite nicely. And in this particular case, we found out that this series diverges. All right, so I got a few more examples for you. I think I got 5 more examples on the next page. And they're going to be doing some root tests as well. So I did the first couple as ratio tests. I'll do a couple more ratio tests, then we'll do some root tests so you can see how that version works as well. All right, so let's charge forward. Okay. So example C, we have n plus 2 over 2n plus 3. So we can more directly just take a limit as n goes to infinity of an plus 1 over an, making sure there's no negative signs. The bottom thing is just n plus 2 over 2n plus 3. It's just the an formula. The top is where I put in n plus 1 instead of just n. So I have n plus 1. Let me make it a little bit easier to read. N plus 1 plus 2 over 2 n plus 1 plus 3. I'm sticking in n plus 1 instead of n for each of those. Move it over here somewhere. Okay. And now we can do our little flippy thing. Maybe a little more space to the right as usual. Okay. So I got my top part being the same. N plus 1 plus 2 is called n plus 3. On the bottom part, 2n plus 1 plus 3. If you want to work that out, it's 2n plus 5. And then the bottom gets flipped, so 2n plus 3 over n plus 2. So we're now finding the limit of this fraction times this fraction. Now you got to be a little careful with your algebra here. You can't just start, like canceling out stuff. These two n's do not cancel out. That's not how math works, right? They have to be multiplied or divided by each other, and they are being added to 5 and added to 3. That is not a multiplication division. It's a combination of divisions and additions. That's not going to be anything that we can simplify. The way we simplify this by multiplying things out. You can now do your distributive property, my foiling, n times this, n times this times this. You can distribute these all out, and then you get one nice thing that you can use L'Hopital's rule on. Now, I'm actually not going to finish this problem because this problem does work well using the ratio test. And when you do the ratio test, you may get something like 1 at the end. And if you get 1, it doesn't tell you anything, right? So we can do this out, and it might be nice just to do it out. I might invite you to do so. But what I want to point out is that you don't have to use the ratio test on everything, right? Even if something would possibly work from the ratio test, and this may not work on the ratio test at all, you could just use any other test like the divergence test. right? The divergence test is a very nice test to use. And let me remind you what the divergence test is. Divergence test. Divergence test is also a limit. So again, we're not looking at the series, we're just looking at the limit of the sequence. But here we're just doing the AN. We're not doing any like fraction or complicated thing. If this limit does not equal 0, we immediately know that the series diverges. That's the divergence test. And let me show you this one. This one here, we're going to do the limit as n goes to infinity of n plus 2 over 2n plus 3. And that is infinity plus 2 over 2 times infinity plus 3. It's infinity over infinity. So we can use L'Hopital's rule. And we get the limit as n goes to infinity. The derivative of the top function, n plus 2, is just 1. The derivative of the bottom function, 2n plus 3, is just 2. What is the limit as n goes to infinity of 1 over 2? Well, 1 over 2 is 1 over 2. The sequence is 1/2, 1/2, 1/2. It doesn't care about what n is. It's always a half. So this limit is 1/2. And again, I will ruin the surprise and tell you that 1/2 is not equal to 0. And by the divergence test, if you have a series and you look at the limit of the sequence and the limit of the sequence is not equal to 0, we know that the series diverges. So very quickly, just by doing one simple limit here, we know this series diverges. So the original series, n plus 2 over 2n plus 3, diverges by the divergence test. So always remember that, you have all those tests. And if you continue doing this one over here, if I go back to my original like ratio test and I start multiplying things out, I'm going to get 2n squared plus 6n plus 3n plus 9 on the top. And I'm going to get 2n squared plus 10n plus 5n plus 10 on the bottom. Oops, I forgot my little limit sign. Throw that in there. If you do the ratio test, you may not get any information. This limit, if you continue doing this limit, it actually ends up being 1. You'd have to use like some division by n squared or use L'Hopital's rule and simplify it, and you get a value of 1. And remember, when the limit is equal to 1, when the ratio of the limit is equal to 1, the ratio test doesn't tell you anything. It has to be either greater than 1 or less than 1. So you definitely can do the ratio test, but sometimes there's easier things to do. And when you're doing the ratio test, if you get 1, you didn't learn anything anyway, so you're going to have to use a different test. So I set up number C to be one in which I wanted you to think about the fact that just because you're in a section which is focusing on the ratio test and the root test, you still haven't forgotten all the other tests, right? And they may be necessary because you may even get a limit when the ratio is equal to 1, and therefore the ratio test doesn't tell you conclusively convergence or divergence either way. Okay, hopefully that strategy of mine to kind of show you not to forget your divergence test and other things like that made sense to you. All right, so let's do a one where it is going to be something that we can analyze using the ratio test. So we have example D. N squared over 2n minus 1 factorial. Whenever you see the factorial things, factorials are notoriously difficult to simplify. It's just, you're getting n times n minus 1 times n. You get all these n's, and it's really hard to multiply them out and do anything with them. So when you see a factorial, the ratio test is golden because the ratio test will always simplify those factorials. And I'll show you this more complicated version of the factorial. I'll show you how that simplifies. So once again, we're going to write out our ratio test ratio. So again, I'll remind you it's a n plus 1 on the top and a n on the bottom. And so in this case, well, the bottom is just the bottom. Bottom is just n squared over 2n minus 1 factorial. And the bottom is where I stick in n plus 1s. So n plus 1 squared instead of n squared. And on the bottom, I have 2n plus 1 minus 1 all factorialized, which again looks really complicated, but do not panic. There's plenty of time to panic later. Let's just do this problem right now. All right, so the top is the top. N plus 1 square rooted, and we have 2n plus 1 minus 1. So just to remind you, 2n plus 1 minus 1 is 2n plus 2 minus 1. That is 2n plus 1, right? 2 times n plus 1 is 2n plus 2, minus 1 is 2n plus 1. So 2n plus 1 minus 1 factorial is the same thing as 2n plus 1 factorial, right? It's just, you're just doing the algebra on 2n plus 1 minus 1. So this is going to be 2n plus 1 factorial. And then I'm going to flip the bottom part and multiply. So it's 2n minus 1 factorial over n squared. All right. And then with factorials, again, I'm going to recommend you write out the terms. I just don't have hardly anybody who has great ideas how to simplify factorials until you've done a dozen or two, right? It's just hard to imagine what they do. You will eventually get the hang of them, and it'll be faster and easier to simplify. But let's cross that bridge later and write them out for now. So I'm going to start with the n squared stuff. So n plus 1 squared, I'll just square it out. It's n squared plus 2n plus 1, and the bottom of n squared, right? So those don't do anything very nicely. They're just that kind of thing. All right. So what is this 2n minus 1 factorial? Well, 2n minus 1 factorial, it starts with 2n minus 1, and then it's one smaller, right? One smaller of that is, well, what's one smaller than 2n minus 1? 2n minus 2. And then 2n minus 3. All the way down to 3 times 2 times 1. It just gets one smaller each time. And the bottom, we have 2n plus 1 factorial. So we'll do that. I guess I'll do that in black over here. 2n plus 1 factorial. So we start with 2n plus 1. And then what's the next term? Well, we get one smaller. So what's one smaller than 2n plus 1? It's 2n. You just subtract 1. And what's one smaller than 2n? That's 2n minus 1. And then 2n minus 2. And then all the way down to 3 times 2 times 1. So now do you see what simplifies here? What cancels out or divides out? All the 1s, 2s, and 3s. 2n minus 2. There's a 2n minus 3 that cancels. A 2n minus 1 that cancels. All those things divide out to equal 1. What are we left with? Well, from the factorial world, we're left with 2n plus 1 and 2n on the bottom. So what did we work out here? We got the limit. Oops, I forgot to write my limit over here. I'm supposed to write the limit every time. Don't let me forget. Okay, so we have the limit as that goes to infinity. What do we have on the top? We have our n squared plus 2n plus 1, and everything else divided out. On the bottom, we have n squared. We have 2n plus 1, and we have 2n. And everything else divided out. So that's what we got. This is a fairly simple polynomial divided by a polynomial. You can do this in various ways. I'm going to do it just by simplifying algebraically. But we just need to find the limit. So the top doesn't really simplify. But the bottom we can multiply out. We get n squared times 2n. So n squared times 2n is 2n cubed. So I have 2n cubed times 2n minus 1. So 2n cubed times 2n is 4n to the fourth. And 2n cubed times 1 is 2n cubed. So you can do more steps if you want and verify that my answer is correct, hopefully. I multiplied n squared times 2n, that's 2n cubed, and then I distributed 2n cubed times 2n, that's 2n cubed times 2n, which is 4n to the fourth, and then 2n cubed times positive 1, which is 2n cubed. All right, so I simplified algebraically, and then you can see what's going on here. We have an n squared version on the top. We have an n to the fourth version on the bottom. In fact, you can already see what's going to be happening, or you can use L'Hopital's rule in simplifying this. But I'll show you a technique that works for polynomials divided by polynomials that many of you learned in a precalculus class. You could just divide everything by n squared. No, you divide everything by the highest power. The highest power is n to the fourth. So we divide everything by n to the fourth. I almost got it wrong. I don't use this method very often because I just use L'Hopital's rule, but I figured this might be a good example to show people in case they had seen it before and needed some reminding of how it works. It only works with a polynomial divided by polynomial, but luckily that's exactly what we have in this particular problem. So I'm literally dividing everything by the highest power of n, which in this case is n to the fourth. All right. So why do this madness? For those people who are not unfamiliar with the technique, why am I doing this? I'm doing this because everything simplifies very simply when you divide by the highest power of the exponent. So what do we get here? All right, so n to the squared over n to the fourth is 1 over n squared, because you have like n times n on the top, n times n times n times n on the bottom. You like subtract the exponents, something like that. So 2n over n to the fourth, one of the n's divide out, so you get 2 over n cubed, and you just get 1 over n to the fourth here. On the bottom, we have n to the fourth over n to the fourth is just 1, because it's divided by the same thing. So 4 times 1 is 4. And the second thing is 2 times n cubed over n to the fourth. So 3 of the n's divide out, leaving just 2 over n. All right, so now that we simplified each of those things, most of these go to 0, because this thing, 1 over n to the 1 over n squared, n is going to infinity. So this goes to 1 over infinity, or 0. 2 over n cubed, well, that's 2 over infinity, which goes to 0. 1 over n to the squared, or I think it's 1 over n to the fourth. I just miswrote it. 1 over n to the fourth is 1 over infinity, and it goes to 0. 4 is a 4, but 2 over n squared does go to 0 because it's 2 over infinity. So what does this limit turn out to be? It turns out to be 0 plus 0 plus 0 over 4 plus 0. And 0 over 4 is 0. So we did the ratio test. We took the ratio of an plus 1 over an over here. And then we wrote out all our crazy things with the n plus 1s in there. We used some algebra to simplify, multiplied stuff out, used more algebra, and we found the limit is equal to 0. And according to the ratio test, if the limit is less than 1, we know it converges. If the limit's greater than 1, we know it diverges. If the limit's equal to 1, we don't know anything. But this is less than 1. This is 0. So we know. So the original series here, which was n squared over 2n minus 1 factorial, converges by the ratio test. There we go. All right. 3 more examples? Yes, 3 more examples, and then the video is over for this particular section. So what do we do next? Well, I have one here, which is -1 to the n over n squared plus 1. So we can, again, use the ratio test. Limit as n goes to infinity of an plus 1 over an. And remember, we are getting rid of all negatives. And if you worked on the previous section, 11.5, a little bit, or watched the video, you'd know that this -1 to the n just is either -1 or +1. It doesn't do anything other than switch back and forth between -1 and +1. So when you're doing this particular limit, that's the part that's going to disappear when we take absolute value bars. Absolute value bars basically says we're getting rid of all the negative signs, making them all positive. So this -1 at the end just becomes 1. So this is going to be on the bottom, we get 1 over n squared plus 1. On the top, we get 1 over, not n squared plus 1, because remember, we're putting in n plus 1 into our formula. So on the top, we get n plus 1 squared plus 1. Right? So for the ratio test, you get rid of all the negative signs, just that's the absolute value bar thing. And you have the limit of this thing. And once again, you can flip and multiply and do all your stuff like that. But this is an alternating series, right? We don't need to do the ratio test because we have a specific test called the alternating series test. So for the alternating series test, you just have to know it alternates, you just have to know it decreases, and you just have to find the limit without having any kind of weird fraction and things like that. So let's try the alternating series test. So does it alternate? So first thing is we have to find out, does it alternate? And the answer is yes, because of this -1 to the n part. -1 to the n just is going to go +1, -1, +1, -1, depending on whether n is an even number or an odd number. Okay, so the first thing you have to see is it alternates. Second thing we have to see is do the terms get smaller? And again, we're just talking about like the positive numbers, right? So the positive numbers here, right? You get 1 on the top and you get n squared plus 1 on the bottom. So remember, we get 1 on the top and n squared plus 1 on the bottom. That's our sequence. That's our an. So do the terms get smaller? And the answer is yes. Yes, because the bottom gets larger. So the fraction gets smaller. Right? Anytime you get the bottom getting bigger, like 1/2 versus 1/5, the bottom is larger. 1/5 is a smaller fraction because it has a larger denominator. And n squared plus 1, you can write out a few terms. If you're not convinced, again, writing out some terms is always a really nice thing. This sequence, when I put in 1, I get 1 over 1 squared plus 1, which is 2. And then I plug in 2, and I get 1 over 2 squared plus 1 is 5. And then I plug in 3, I get 1 over 10. Plug in 4, and I get 1 over 17. So you can see that the bottoms get larger and larger and larger. When the bottoms get larger, larger, then we know that the fractions, the numbers get smaller. So do the terms get smaller? Yes. So it alternates, yes. The terms get smaller, yes. The last thing we have to do is take the limit as n goes to infinity of the sequence and see if it goes to 0. It's question mark, right? We have to see if it goes to 0. So what is that limit? Well, the limit as n goes to infinity of 1 over n squared plus 1 goes to 1 over infinity, which is equal to 0. So the answer is yes. So alternating series test is a pretty easy one to do. And you don't get the bad thing, like if you get 1, it doesn't tell you anything. It always tells you something, right? So we know that it alternates. We know the terms get smaller. We know the limit goes to 0. So we know it converges. So we're done. We don't have to use the ratio test on this one either. And if we did, there's a good chance that we would have gotten 1 as our ratio, our limit of the two ratios. So this series here, -1 to the n over n squared plus 1 converges by the alternating series test. All right, let's do a couple of root test examples. So I'll just remind you about the root test. For the root test, what we're doing is we're taking our we're taking the limit of our sequence raised to the 1 over n exponent. So we're doing an, our sequence, raised to the 1 over n. And we take the limit as n goes to infinity. And once again, if you get less than 1, our series converges. If this limit of the sequence is greater than 1, we know our original series diverges. And if it's equal to 1, we don't know anything at all. All right, so let's see a couple examples of the root test in action. All right, G is in the way of my solution space for F. So I'm just going to write G down here. N equals infinity, n equals 1. And then we have sine 1 over n over 1 over n to the nth exponent. Okay, so I'll just do G down there. So I have space to write my F in here. All right, so F, let me zoom a little bit here. Example F is n to the n over 3 to the 2n plus 1. Now, you might try something like the ratio test on this one, but when you stick an n plus 1, you get n plus 1 to the n plus 1 exponent, which is difficult to simplify, even if your algebra skills are very strong. It's just not fun to try to simplify a variable raised to a variable. It's just tough. We like numbers raised to variables or variables raised to numbers. Those are nice rules to simplify. Variables to variables, not so nice. When you have a variable raised to a variable, like n to the n, that is a good time to use the root test, right? You have a variable raised to the variable, like n raised to the n. Consider root test. The root test doesn't come up very often. The ratio test comes up a lot. The root test does not come up very often because it's really only kind of a niche usage. It only is when you have like a variable raised to a variable, which doesn't happen very often. So in this case, I set it up. We have n raised to the n. That's a variable raised to the variable. So we're going to use the root test. So what does the root test say? The root test says we take the limit as n goes to infinity. We take the sequence and we raise it to the 1 over n exponent. So what does that look in our situation? So that looks like, well, our sequence is n to the n over 3 to the 2n plus 1. And all of this is raised to the 1 over n exponent. Okay, so now we have to simplify this. But as I said, these do simplify nicely, assuming that you have like variable raised to a variable things. So what do we do if we have some exponent type thing raised to an exponent thing? Well, first of all, we have a fraction. So for a fraction, if you remember, we can raise each part to the 1 over exponent. So n to the n to the 1 over n, the top part raised to the 1 over n, and the bottom part raised to the 1 over n. Each of these parts can be raised to the 1 over n. And then what do we do with each of these? So for the top part, we have n to the n, which is an exponential type thing, raised to the 1 over n. So if you remember all those formulas for simplifying exponentials, when you have an exponential raised to another power, you multiply those powers together. So you still have the same base, n, and then you have n times 1 over n, which is just 1. So here, when you have n to the n and you use the root test, that exponent of n raised to the 1 over n all just becomes 1. On the bottom, we have 3, and again, we multiply exponents, so 3, 2n times 1 over n. So maybe I'll just write this as 1, just so that people can see what's going on here without having all the little steps written in there. 2n times 1 over n is just 2, and then 1 times 1 over n is 1 over n, like that. Okay, so we're just multiplying out the exponents. Okay, so now we have n on the top and 3 to the 2 plus 1 over n on the bottom. So what happens as n goes to infinity? As n goes to infinity, the top part goes to infinity to the 1, which is infinity. The bottom part goes to 3 to the 2 plus 1 over n, and this is 3 to the 2 plus 1 over infinity, because n is going to infinity. But 1 over infinity is 0. So this is infinity to the 3 to the 2 plus 0, or just 3 to the 2 power. 3 to the 2 power is 9. So we have infinity over 3 to the 2 power. So infinity divided by 9 is still infinity. So this limit of the an to the 1 over n exponent is equal to infinity. And our benchmark is whether it's less than 1 or greater than 1. This is greater than 1. And according to our root test, if you have forgotten, I'll flip back here real quick. According to the root test, if you do this limit and you get something greater than 1, we know that the original series diverges. That's called the root test. So we just found out that the limit is greater than 1. Pardon me. So this original series, which is 3 to the 2n plus 1 on the bottom and n to the n on the top. This thing right here, if you want to put the numbers in there, this thing diverges by the root test. We did the limit of the 1 over nth root, and we got an answer which is greater than 1. So we know that the original series diverges. All right. That's an example of the root test. And let's do one more of those here in my last example. For example, G. You can see, again, I have an exponent of n, and I have a base that has n as, so I have a variable like 1 over n raised to the n, or sine 1 over n raised to the n. So this is a variable raised to a variable. So we're going to try use the root test. So root test. So I'm going to do I'll use green this time. I'll use black this time. I'll do the limit as n goes to infinity of this sequence. That's my original sequence. And then I raise that to the 1 over n. And very nicely, the nth exponent and the 1 over nth exponent, when you multiply them together, it equals 1. So this is the limit as n goes to infinity of sine 1 over n over 1 over n. Okay, and so now we need to figure out the sign of this. So the 1 over n, sine of 1 over n, is equal to, well, 1 over infinity. 1 over infinity is 0. And then 1 over n on the bottom is, well, 1 over infinity, which is also 0. So we get sine of 0 over 0. Well, what is sine of 0? Again, you can grab your calculator, or you can sort of remember your trigonometric facts. Sine tells you the y value. If you're at 0 radians, which means you're still stuck on the x-axis, the y value is 0 there. So this is 0 divided by 0. All right, so we know that this is an indeterminate form, so we can use L'Hopital's rule to simplify it. So from here, this thing right here goes to 0 over 0. So we're going to use L'Hopital's rule to simplify it. So we can use L'Hopital's rule. The derivative of sine is cosine. But I have to use the chain rule. Cosine of 1 over n times the derivative of the inside function 1 over n, which this is 1 over n is n to the minus 1. So I get negative 1 n to the minus 2, or negative 1 over n squared. On the bottom, I also have 1 over n, so I also have negative 1. So the derivative of 1 over n is negative 1 over n squared, negative 1 to the negative 2. And once again, I forgot my little limit thing right here. Okay, so very nicely, this 1 over n squared and 1 over n squared, they divide out to equal 1 because they're the same thing divided by each other. And we get the limit as n goes to infinity of cosine 1 over n. So this goes to cosine of 1 over infinity, which is cosine of 0. And what is cosine of 0? Well, 0 radians, x-axis, it's equal to 1. So this series, when I use the root test, I get 1 as the answer. So what does that tell me? You may know, but I'll review with you. If you have a series and you do the root test, and the limit of that root is equal to 1, we don't learn any information. So unfortunately, we did all the right steps. We did the root test. We did the series raised to the 1 over n, and we did the limit, and we simplified it, and we got an answer of 1. But when you get an answer of 1 using either the ratio test or the root test, you don't learn any information. So we're going to have to evaluate this series using a different technique. Okay. 1 second. All right, so what are we going to do here? We tried the root test, and it didn't tell us anything because the limit was 1. So we could try the ratio test, or we could try a different test. I'm going to suggest we try the divergence test. It's always a great test to use because all you have to do is just find a limit. And if the limit does not equal 0, you're done. So we're going to try the divergence test. Divergence test. What is the divergence test? Well, I did it before. You may remember. We just take the limit as n goes to infinity of this crazy thing. And we see if it equals 0 or not. If it doesn't equal 0, then we're done. We know that the series diverges. If you're adding up numbers that are non-zero forever, you're going to get some version of infinity, no matter what. Even if they're small numbers like 0.1, if you keep adding 0.1 forever, it's going to add up to infinity. That's the idea behind the divergence test. The limit has to equal 0, otherwise we know it diverges. So let's simplify this. The 1 over n on the bottom, that's a fraction on the bottom. We can write that, we can flip that and multiply. We can write that as n on the top. So this is the limit as n goes to infinity of n times sine 1 over n to the n. And as I've suggested in previous speeches, previous examples, we should write out some terms. Let's see what happens when we write out some terms. So let me see if I can get this to do what I want it to do. All right, it's not working right now, so it'll be fine. I'm trying to get the page to expand, but it's not working. All right. Don't know how to fix it for now, so I'll just ignore it. Okay, so let's write out some terms. This is going from n equals 1 to infinity. So let's write out n equals 1, n equals 2, n equals 3. Let's write out some n numbers, see what happens. We're going to use this simplified version instead of the original version. Okay, so this is going to be 1 times sine 1 to the 1. And the next one's going to be 2 times sine of 1/2 squared. And then again, we're going to plug in 3. So sine of 1/3 times 3 cubed. And you can kind of see what happens here. 4 times sine of 1 over 4 to the 4th. So sine is a value that does not get bigger than 1, right? It goes between -1 and +1. It never gets a different value than 1 or -1. So here we're getting 1 times some number raised to the 1. So this is going to be sine of 1 is smaller than 1. So it's going to be some fraction. This is something like sine of 1. We can figure out what sine 1 is because we can go to a calculator and we can just type in, I'm going to move me over there, 1 times sine of 1. And it's some decimal 0.841. So that's going to be some decimal type thing. What about sine of 1/2? Well, sine of 1/2 is again going to be some fraction, but it becomes 2 squared. This is 4 times some fraction, right? This is going to be some fraction here smaller than 1. This is 4 times some fraction smaller than 1. This is 3 to the third. This is 27 times a fraction smaller than 1. 4 to the fourth is 256 times a fraction. The only way these things are not getting bigger and bigger and bigger if these fractions are getting infinitesimally smaller, so that when you multiply 256 times this fraction, you're not getting you're getting a number closer and closer to 0, right? So that's what's going to happen. But we can see that's not going to happen just by looking at, again, our calculator. This is n times sine 1/n to the n. So let's put this as a formula. We're going to use x's instead of n's if you don't mind. So n times, well, I'm going to put parentheses here. So n times sine of 1/n raised to the n exponent, x exponent. So that's sine, that's n times sine 1/n to the n. I used x's because Desmos likes x's. What don't you like here? Oh, I don't have an equal sign here. Equals. There we go. So you can see how kind of crazy this graph is going to be, but I don't want a graph. I just want a table. So I'm going to make a table here. I don't want starting with negative numbers. I think according to our formula here, it starts with 1. So I'm going to have my table start with 1. So let me get rid of this stuff here and start with 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see that sine x times, or x times sine 1/x to the x, it is not getting closer and closer and closer to 0. It's 0.8, 0.9, 0.94, 0.95, 0.96, 0.97, 0.98, 0.99, or 0.98. It's going to go to 0.99 next. You can kind of see what's happening here is this limit does not go to 0. It kind of maybe goes to 1. You could maybe make that argument, but it does not matter. It does not go to 0, right? So from the table, from Desmos table, this limit here does not equal 1, does not equal 0, right? Again, we don't have to know that it equals anything in particular. We just have to know that it doesn't equal 0. And you can continue this on for as long as you want. And you will see that it does not ever get smaller. It gets larger and larger. At least it gets larger and larger and closer to 1 or something close to 1. Maybe it goes past 1. It does not matter. It does not go to 0. So for this particular problem, we have a sequence of sine 1/n, sine of 1/n divided by 1/n, all raised to the nth power, which we simplified a little bit. And this limit does not go to 0. So what does that mean? So if you have a series where the sequence has a limit doesn't go to 0, we immediately know that that series diverges because of the divergence test. I don't have any more space here because I did something wrong and maybe I used too much space already, but my writing program doesn't let me expand the page anymore. So I'll just have to write my conclusion over here. Conclusion. Then my conclusion is this original series, which was sine 1/n divided by 1/n, all raised to the nth power. This thing diverges. I'll just write a different color just so it stands out. Diverges by the divergence test. Okay, so there's a couple examples of the root test. One that actually was successful, one that got a limit of one, didn't tell us much, but we had to use a different argument, in this case, the divergence test, to try to determine whether it converged or diverged. So ratio test, root test, those are the ideas behind this section that we're working on, as well as some other conditional and absolute convergence that I covered in the previous video. Okay, so hopefully this video was helpful. Let me zoom out a little bit so you can kind of see the stuff I wrote here. And there we go. Screenshotable now, I think. So if you have any questions, please do reach out. Let me know so I can help you understand this. And I do hope you have an enjoyable day, and perhaps I'll see you in the next video.